my screen capture thing there, so we should have all this up and running. So who are we missing? We're Chris C, and Alicia. And Nick.
We're missing the birthday boy. Wow.
Whose birthday is it?
Chris's birthday.
Okay. He's probably drunk.
Yeah, knowing Chris, yeah. How many video games do you think he's played since you left, CJ? Oh my god, an absurd amount, I'm sure.
I was pretty so early on. I broke the Wii out of the closet and went through, and I beat the original 8-bit Zelda, so that was good. Both quests, not without assistance. I did use Google to sort of find my way around things, but
Chris and I actually we did a trade. He had to read one of my books, and then he got to pick a video game for me to play, and so he's having me play the Zelda, I think Wind Waker or something.
Okay.
Wind Waker, yeah. So I just started that.
What platform is that on?
That's not one of Chris's things. I don't know. I'm not too good with the stuff. Although I did just bring out my my Wii as well.
Okay.
I'm gonna play Mario Party.
Nice. Yeah. I've got a Nintendo 64 hanging out. I might break that out and play some Bond.
Yeah, do it.
Yeah.
GoldenEye?
Yeah. I occupied a good portions of my time as an undergraduate. All right, I think we got oh no, we're still waiting for Chris. Okay. There he is.
Happy birthday.
Happy birthday.
Man.
Thanks.
I'm Chris C. I'm gonna arrive fashionably late on my birthday.
Oh, it was 2:09.
You're the last one. I was
talking to my mom on the phone if it makes it better.
Don't blame it on your mom. Nice try. All right. Well, good to see everybody. I guess first question, for anybody who didn't have SPSS on their personal computer, were people able to go through and get that through IBM's website so that they have a copy there? Cool. All right. Yeah, I was having nightmares on what trying to connect through the remote desktop would look like. That was going to be a disaster. So that's good. Any questions on, and I don't know if has anybody started on the problem set 3? Haven't, so okay. So go through and get started on that. I mean, we should be, by the end of class today, have everything that we, DJ or something like that. We should have all the material that we would need to get you worked through that. But if you have questions and are running into problems as you're working through that, just email me. We can use screenshots. I'm not going anywhere, so I'm happy to connect via Zoom and talk, sort of video chat and things like that. That's sometimes going to be easier than going back and forth and stuff like that. So do that. This is an individual problem set, but you can utilize one another in terms of resources and things. The only thing I would say is be careful, just because a lot of maybe some of your stuff is going to be just back and forth via email and things like that. Just try and avoid falling into a trap of just making sure your words are your own words and not sort of get into it. I could see it being easy to, like, oh, I'm talking with Alicia, and Alicia's like, oh, this is kind of how I'm interpreting something, and then kind of getting into something that's very similar. So we're going to do the best that we can, but just try and be mindful of that type of stuff. Does that sound all right? Cool. All right. People went through, and it looked like there was either you all went through and watched the rest of the slides, or I got a small following on YouTube independently where people just decided to jump on and watch that. I suspect not. But thank you for going on, watching the rest of those, the screening procedures. Any questions before we get going on the actual kind of walkthrough in SPSS?
I was a little confused about the variance inflation factor.
Okay.
I'm not entirely sure what that is.
Okay, cool. So we'll make sure when we get there to spend some time talking about exactly what's going on with that piece. So that's good. Any other portion of sort of working through residuals and discrepancies, leverages, influence points that people found to be kind of confusing? Okay, cool. So we'll go through and just take some time and work through stuff. So as we're doing this, I think we'll probably be okay. I see most of you have your mic muted. That's probably good. But again, that space bar is a nice way. So like CJ, I see your thing is on. Just hit that space bar, hold it down, and talk. Well, you got to hold it down. And there we go. Okay. Yeah. So it's basically walkie-talkie function, right? I think that'll be nice because then you won't have to click back and forth. You can just go through and hit that to unmute your mic. And I'm going to try to do the best that we can to use this just like we would in class. So I'll go through and be asking people questions and things along those lines. And so if you're talking and forget to hit your mic, I'll just say, hey. Well, you can hear me. I'll just say, hey, Mike, something like that. So does that sound good? Okay. Questions or concerns about what we're doing in terms of schedule, where we're going, any of that type of stuff? Okay.
What does the next problem set do?
We'd be flexible. So technically, sort of if we were on target, we would say that it would be due next Friday, which is probably a reasonable amount of time. I mean, this one, the screening will be probably the thing that takes you the most time to work through, but just straight standard multiple regression, hierarchical regression, those models are pretty easy to run and interpret, so it'll be not nearly as complex as the last one. So aspirational goal, let's try for next Friday at noon to have that done. We won't be all the way through moderation. It'll take us a couple classes to get all the way through moderation because moderation gets a little bit complicated. But it's also nice, I think, for you guys, right, if you don't have these problem sets back to back. So trying to space that out to some extent. Does that sound all right? Okay. But we'll just play with it and see what we can do and what makes sense with timelines and things. Cool. All right, so I'm going to go through and do this.
Another question.
Oh, yeah. What's up, Chris?
So how will we be getting problem sets back?
Yeah, that's a good question. So I'm working right now. All right, can people see my full screen now? Okay, cool. So, yeah, we should just be able to work through here. For problem sets, so I've gone through problem set 2 was looking good. Laura's gone through, done an initial run through that. I'm just finishing up scoring. I think what I'm going to do is, if this sounds acceptable, it's not sort of perfect, but what I'll do is I'll go through and so long as I can get into the office, I'll just scan your problem sets with my handwritten notes and stuff like that, and then just ship them back to you in a PDF, so you should have feedback, all that stuff. And then when we all get a chance to get back together at some point in time, we'll pass off hard copies. Does that seem like a reasonable solution? Cool. All right. So, yeah, we'll see. So as long as I can... We were just talking, I wouldn't be surprised if eventually they shut down the university, just lock the whole thing so no one can get on, particularly if things start to ramp up. But if we hit that point, I can go through and summarize feedback on individual problems and things like that if we get to that point. So we'll find a workaround. Sound good? Cool. All right. Yeah.
Are we going to still have 4 homeworks? And then can you tell us a little bit about what the final exam is going to look like?
Yeah. Let's not worry about the final exam at this juncture. Okay. We'll go through and do our best to work through the skills that I think are going to be important. So we're going to have work through moderation. That's going to be pretty complicated. Mediation won't be too bad. And then we got some ANCOVA stuff we'll hopefully touch on, and some logistic regression. And so we'll just kind of see sort of what that evaluation, that semester evaluation might look like as we move forward with stuff. Does that sound good? Cool. All right. So people have their regression set open in their windows. Everybody up and running there. And then also our standard multiple regression, the screening, this handout. This is the one we're going to be working through. So this will be your reference guide. Unmic and chime in, because I can't see Tamara or Nick or Siley. They're not in my lineup here on my photo strip lineup. But did anybody go through and look at the screencast with the SPSS screening?
Yes.
Okay, a couple people. All right.
Yeah.
Okay, good. That's going to be, the sound is garbage. I've got a new mic that came in. It's hard to sort of, ordering things in a pandemic can be tricky, but I've got a new mic, so screencast from here on out, sound quality is going to be better. But that's going to be, did people see that I was able to go through and put in timestamps on that video? Okay, so if you go to that video, because it's long, I mean, there's just a lot to go through with these screenings. But if you open up that video and go down to the description and sort of open it up, what I did is I put timestamps on sort of different tasks. So you can go through and take a look at that. And let's say you're just struggling with discrepancies or trying to remember what that's about, you should be able to go through. And if you look at the description, go down the show to find the full description, you'll see I've got a timestamp on there that you can just click at, and it'll take you right to the video, the section of the video where we start talking about discrepancies. So that way you're not having to start at the very beginning and then poke around and try and figure out specific things if there's specific aspects of this you have some difficulties with. Sound good? Cool. All right. So let's start with working through this actually in SPSS. So here we've got our data set, and here's our worksheet. So again, the data that we have here and the question that we have is wanting to know what the impact of PTSD, chronic pain, opiate use, the unique effects of these individual predictors on this continuous measure of role functioning. Okay, so this is just adaptive functioning in day-to-day life stuff. And so our PTSD variable is continuous, right? So range 0 to 136. So these are community survivors of motor vehicle trauma. So these are going to be people who have been in bad car accidents and coming in for assessment. So we've got a measure of PTSD. We've got a continuous measure of pain, ranging with scores ranging from 0 to 6. And then we have opiate use. Opiate use is dichotomous variable, so it's 0, 1, yes, no. And in our regression models, we can have our predictors can be continuous or they can be dichotomous. Anytime you're coding dichotomous indicators in the context of regression, always code them 0, 1, where 0 is your reference group. That's going to make your life a lot easier, and it's going to improve interpretation. So here we have individuals who either are or are not taking opiate medication, and then our role functioning we're presenting it here as ranging from 0 to 100 continuous scores. And right down here, this is going to be our regression equation that we're going to be estimating. So what we want to do is we want to regress role functioning onto pain, opiate use, and then PTSD. Okay, so questions in terms of the setup, what we have in terms of our data. Okay, cool. So going up to our set, we've got our participant number in SPSS. We've got a measure of pain, opiate use, PTSD, and here's our role functioning. Okay, so Alicia, what's the very first thing that we want to do as we start to jump into our screening?
Sort so that you can look for missing values.
Yeah, I want to go through and take a look for missing values. And if I'm doing that in SPSS, pretty easy. If I just go to pane and right click and then hit sort ascending, okay, that'll go through. If I have any missing values, it's going to kick those right up to the top. Looks like it's fine. Don't have any missing values here, so I'm going to be feeling like I'm pretty good to go there. Okay. If I were, though, sometimes if I have a big model, right, and if I've got a lot of different variables and so I'm missing values kind of all over the place, one of the things that you can do, if I go to Analyze, Descriptives, and I say, okay, so the variables in my model are going to be pain, opiate use, PTSD, and role functioning, so all 4 of those, and I just kick those over and I hit Paste. What I can do to very quickly identify if I'm missing, if I have any case that's missing a variable in that set, I can go compute, and then if I had a check equals my variables here, and I'm just creating a new variable that's pain plus opiate use plus PTSD plus role functioning. Then I put a period at the end and I tell it to execute. Okay, what this is doing, this is just creating a new variable that's the sum of pain, opiate use, PTSD, and role functioning. So I don't care about the value, but if I have any case that's missing one of these values in this addition statement, it's not going to come up as a value. It's going to my check variable is going to have a missing value in there. So if I go through and I run this, why is that? Sort of arrange this a little bit better. Okay, so here I can see I have a check variable. And if I go through and I sort ascending, I see that I don't have any missing values there. So this can be a helpful way if you're running a series of analyses where you're maybe running a bunch of models and have different sort of combination of variables and things like that. This is a nice way to go through and see, okay, what's the set that I have full information on, as opposed to, particularly if you have a lot of variables, going through and sorting individually and then trying to keep track of who's got what stuff where. Okay. Questions on that? All right. So we don't have any missing values, so that's good. What we want to do now is go through and take a look at skew, kurtosis, indices, and plausibility things. So I'm going to go, actually, we got it. So, well, I'm going to go Analyze, Descriptives, going to go back to Descriptives. I'm going to hit Save Standardized Values. I'll go to Options, Skew, kurtosis, and paste that in there. Get rid of that. All right, and again with these screenings, remember that if you go through an asterisk stuff, you can put in comments. This is going to be super helpful in setting up this syntax file because you're going to have to do a lot of these. But if you've got a good syntax file, you don't have to work through menu stuff all the time. You can have this and just swap out variable names and things. So I might say, looking at descriptives and plausibility, something like that, so that you can to remind yourself what's going on with each one of these. Okay, so I'm going to go through and run this. All right. And Tamara, can you tell me what we have going on in this example here?
Yep. So it looks like our skew and kurtosis values, for the most part, are okay, except for roll functioning is a little bit higher.
Yeah. So if I'm looking at, and again at this point, having done a bunch of screening from last semester, anytime we get a skew that's above 2, you know, probably when we graph that, that's going to be pretty strong, right? Again, our general rules of thumb is going to be like, oh, if it's skew or kurtosis values below 2, we might not be super concerned about that. But here we've got a kurtosis value of over 4, a skew value of over 2, so we know that we're going to have some problems there. Okay, Chrissy, what else do we want to take a look at in this table?
On this table,
Yeah.
we talked about skew and kurtosis.
Mm-hmm.
Plausible values.
Yeah. Do our values all look plausible here?
As far as I know. I think so.
To my knowledge.
I don't know what the roll functioning is out.
All right. Well, if we pop up here, right?
Oh.
Right, there we go. We go through and we take a look. We see that PTSD should range from 0 to 136. PTSD 0 to 111, so that's good. Pain 0 to 6. 0 to 6 here. Roll functioning 0 to 100. 0 to 100 there, so that looks all right. And then I shouldn't have included opiate use as my continuous variables, but I'll go through and paste that and look at opiate use separately. Okay. Chris, you want to finish up with opiate use? What are we seeing here? I think you're unmute your mic. You're muted. There we go.
We have really similar cells.
Yeah.
Cell size.
Yep.
101 to 100.
Yep. So this is good. We've got a nice balanced design, at least in terms of our dichotomous variable, pretty even split. That's exciting. Values of 0 and 1 in terms of our plausible values, so we don't have anything falling out of bounds there. So we're feeling pretty good about things up to this point. Remember that when we're thinking about univariate outliers, we can have univariate outliers in our categorical variables. If we have like wildly uneven splits on the order of like 10 to 1, that would qualify as outliers even on a dichotomous variable, just with that type of stuff. And we have problems with attenuating correlations and things along those lines, so we want to keep an eye on that. But for these data, things are looking all right. Okay, with the exception, as Tamara noted, skew and kurtosis. Okay. Questions about what we've done up to this point? These are things that we've done before, so we're not too concerned. All right. So what I'm going to do is I'm going to go to Analyze, and I'm going to go to Descriptives. I'm going to go to Explore. Okay. And here, I'm going to take my continuous variables. So I got pain severity, PTSD, and roll functioning. I'm going to label cases by subject number, right? So that on my box plots, things that are falling beyond 1.5 times the interquartile range, 3 times the interquartile range are going to pop up with subject number. Makes it easier for me to identify them. And then in plots, I'm going to request histograms, turn off stem and leaf. Stem and leaves are nice, but they're just not quite as clean for what we're doing here. And then I'm going to go ahead and paste this. Okay. And again, you can go through and say plotting distributions. Okay. So I'm going to go through and run examine to give me my plots here. All right. And if I scroll down, Siley, what do you think about this pain histogram? Siley, is your mic on?
Hello?
Oh, there we go. Okay, cool.
There's a little bit of skew,
Yep, a little bit of skew.
but it's pretty normal, I would say.
Yeah, it's not too bad, right? And again, we've got a good sample. We've got 201 individuals here. We've got kind of some weird, it looks like with the scaling, some gaps in this distribution. If I go to my actual data and I look at my pain variable, Siley, is there anything that you're seeing? What's going on with this pain variable in terms of the scaling and the actual scores? Nope, you're not. You're still muted. Oh, hit your space bar. There we go.
So the scaling, it's a 0 to 6, so it's not, there's not that much of a range in it.
Yeah. And if we go down through and we take a look at the individual values, right, it's not a true continuous scale. We've got values in terms of 1/3, right? And so that's what's causing SPSS to kind of do kind of a weird little gap thing here. But in general, are we too concerned? Are we very concerned about our pain variable here, Siley?
No, I'm not concerned about it.
Okay. Same thing with the histogram. If we go through, we see some values that are some low pain values, right? In our screening, we might want to keep track and sort of say, oh, here's some low values falling beyond 1.5 times the inner quartile range, but nothing too bad. Okay. Nick, tell me what we're seeing with this PTSD scale.
So the PTSD scale looks pretty normal.
Yeah.
Maybe potential for maybe like one outlier there towards the above 100, but it looks solid.
Yeah, looks really good. This is really gorgeous, wonderful data that we rarely see in real life, but a really nice distribution. Maybe a high value out here. And if we go down through, we can see in our box plot, case number 221, looks like it's a little bit elevated, but for the most part, probably not too concerned about stuff here. Okay. And then CJ, what about our row functioning variable? BJ, you unmuted your mic? There we go. No, you can't. Hit your space bar.
I'm
There.
hitting the space bar. All right, now is it working?
Yeah, you gotta hit it and hold it.
Yeah.
Okay.
That's what I was doing. It worked this time, but
Okay.
Here we go. So yeah, in this histogram we just see the skew, positive skew and kurtosis that we talked about earlier, and quite a few scores falling at 0.
Yeah. And if we go down through, so we have clear positive skew, got kind of an L-shaped thing going on. And if we look at CJ, what's going on with this row functioning box plot?
Kind of a weird looking box plot. Quite a few extreme values here, and then our inner quartile range and the median are all at the same spot down at 0.
Yeah. So basically, if we go through and we take a look at our histogram, almost everybody in the sample, or over 150 people in the sample, are registering 0 in terms of their overall row functioning, suggesting severe limitations in terms of their overall functioning level. And because in our box plot, the mean, the median, and the median and the first and the third quartile are all 0, that means anything that's not 0, it gets registered as an asterisk going up. Sean, what's weird about this data here?
I guess I don't know what you mean by weird.
Yeah. So we said that we have a continuous measure of row functioning ranging from 0 to 100. Is that accurate? Ignacio, you're shaking your head. What do you see going on here? What's that?
I believe it is very skewed towards the right, and I don't see how. I'm not sure it will be normal. So I'm not sure you will be able to run a regression on these slides.
Yeah. So if we look at this, anytime I see a distribution looking like this, I start to become very suspicious that what I actually have is a continuous variable. If I go up to my data and I sort my role functioning variable, Chris M., what am I actually seeing here?
What you're seeing is a result of the sample that you have.
Yeah.
The majority of people have PTSD, so their functioning is very low.
They're very low.
Ultimately comes out to be some sort of like weird categorical variable.
Yeah. And in terms of my level of measurement, right, even though my scores range from 0 to 100, I don't have a continuous measure, right? My scores fall at 0, 25, 50, 75, and 100. So, and if we actually look at this scale, even though the lowest score is 0, the highest score is 100, what it's actually is a categorical, an ordered categorical variable where I have people at 5 different levels, right? So the score on role functioning can't actually take on the whole range. It's just 1, 2, 3, 4, 5. Here we've got people who are seeking help. They're impaired with PTSD and pain. So most people are scoring on the low end. But what we've got here is then some people who have some higher level of reported functioning. Okay. So, and then our box plot is kind of a mess here. So what we're actually seeing, even though we had said that what we have is a continuous outcome measuring role functioning, is that what we're actually measuring, Sean?
No, you actually have 5 different bins.
Yep, just 5 different bins. And so this creates a pretty kind of substantial problem for our data, right? For our regression models, we're assuming that our outcome is a continuous variable, and sometimes we treat ordinal data as continuous, but here what we've got is something that with everything's really kind of stacked up at 0, and then a small handful of cases that sort of go on above this. Okay, so really at this point in time, if we're being responsible data analysts, we probably would start looking at a different model than a linear regression. Okay, Nick, can you pop up here?
What's up?
Say hi, Nick. Right. So this is these types of data. This is often for like substance use stuff, right? This probably might look familiar to you. This is often what our data look like when we're looking at things like, substance use and things along those lines, or maybe different type of clinical eating pathologies or something along those lines, where most people are at 0, and then we've got some people who do have some stuff, right? So really what we probably ought to be doing, given the level of measurement of our outcome variable for these data, is what we should be doing is looking at some sort of zero inflated regression model or something like that addresses categorical or count values with disproportionate number of zeros and things along those lines. Okay, but we're not going to do that. We're going to pretend that regression is what we're going to go through, and so this is not great, but we've got a skewed outcome. And if we're going to treat it and pretend that it's continuous, what might we do to address some of this? Yeah, Chris.
Log transform.
Log transform. So what we're going to do is we're going to see what happens if we apply a natural log transform to this. Okay, because right now our skew and our kurtosis values for this, in addition to it not being a real continuous variable, our skew and our kurtosis value is also super ugly. So what we want to do is try and do something to bring some of this in. Okay, so what I'm going to do is I'm going to go to analyze, not analyze, transform, and go to compute variable. And what I'm going to do is I'm going to create a new variable. I'm going to call this natural log of roll. Okay. And I'm going to say natural log of roll is equal to, and if I go on my function group and I click arithmetic, it's going to give me a whole bunch of different functions here. I'm going to find ln, which is my natural log. I'm going to double click that. And so this is saying, SPSS is saying, okay, so your ln roll is going to be equal to the natural log of something. Okay. So I'm going to drop in natural log of my roll functioning variable. And that's going to give me the natural log transform of my outcome. Okay. Except for what, Chris M?
Because there are so many, 0 is an option, so you need to add 1.
Yeah, yeah. Because if I try and take the natural log of 0, I'm going to get an error. It's going to give me wrong values. But if I go through and I take the natural log of my roll functioning variable plus 1, that makes my lowest variable, or my lowest value 1, my highest value 101, and then I can take the natural log of that. Okay. So I've got my roll function, natural log of roll functioning is equal to the natural log of my roll functioning variable plus 1. I'm going to hit paste. If I go up and I can see here, I might say transform roll functioning due to Skew and Kurtosis, something like that. Okay. Questions, anybody, in terms of what we've done or how we sat this, how we situated this in SPSS?
Why close 1?
Well, because if we go through and we see that for my roll functioning variable, I've got my minimum value is 0, and mathematically I can't take the natural log of 0, so we just add 1. It's just a constant, so it's just so we can run our transform. Other questions?
Do you generally use log for transformations for regression?
Yeah.
Regression screening, or do you use others? And how do you know when to use others?
That's a good question. Siley, is that you? It sounds like you. Yeah. So again, with which one of these do the screening? I think, yeah. Yeah. So if you look back through your slides, looking at common transformations, right? So with a positive skew, a natural log transform is actually kind of nice, and we'll talk about that later in the lecture about the concern. What's the concern with just blindly transforming variables? Nick?
So when you just blindly transform 1, you lose some interpretive values. So being smart about weighing those different possibilities.
Yeah. So if I go through and I transform a variable, that can be very good things for my model. But now all of a sudden I'm not talking about income in dollars. I'm talking about the log transform or the square root transform of dollars. And the square root transform of dollars is a hard thing for me to understand. I don't know what that means, right? So we want to be careful and only transform when we need to transform, really, because it starts to impact interpretation. But the nice thing about our natural log transform is what this does is it retains some interpretive properties. And essentially what I can start doing with my log transform is talking about my coefficients as given a unit increase in X, a percentage change in expected Y, or given a percentage change in X, a corresponding change in Y. And so natural log transforms, if those are nice, if those work and bring things in line, those are nice options to use. But sometimes they won't. Sometimes our data is going to be doing stuff that requires more of a more extreme transform, like an inverse transform, to use a square root transform, things along these lines, right? And so you have to play around with it, really go through and try and figure out which transform goes through and maybe gets your data back in line. But for these, we have some positive skew. We're going to try a natural log transform first because that just helps retain some interpretive value. Okay. Does that help, Siley?
Yes, thank you.
Okay. Any other questions on our transforms?
Josh, would you consider using dummy variables in this?
Yeah. I mean, you could absolutely. I mean, with this is another option. Again, with these types of data, and there are certain areas, which is why I called up Nick with like substance use. So you often see this type of thing. Really, multiple regression is not a responsible approach to these data. What I could do is I could just transform this into people who have low levels of functioning and some levels of functioning, and just turn that into a dichotomous variable and then run this as a logistic. I mean, that's based on whether or not you can, in good faith, say that anybody who doesn't score a 0 on this measure is reasonably the same. That starts to get questionable. The nice thing is we have zero-inflated models and things along these lines that account specifically for these types of data. That would be my preference. But yes, given what we have here, probably dummy coding this and running this as a logistic is probably a better option than what we're going to do for the purposes of the demonstration. Does that help?
It does, thanks.
Cool. Any other questions on this? All right, cool. So let's go through and we'll create our dummy or our natural log transform. And so if we go take a look at our at our data, we see down here we've got our natural log of our role functioning variable. And so what I'm going to do is I'm going to go back up and I'm just going to steal my syntax statement here and put it down, because what I want to do is I want to get my descriptive statistics now for my natural log of role functioning, and I still want to save Z-scores, want to get skew kurtosis values. People see what I did there? Just trying to streamline things so we don't not always having to go through the pull down menu. Okay, so we're going to go through, do this, and run. All right. And Alicia, can you tell me what are we seeing here when I look at skew and kurtosis values for the natural log of role functioning?
They're more within acceptable ranges.
Yeah, right. So our skew was over 2. Now it's under 1.5. My kurtosis was 4, and now it's sort of just barely above 0. Are we happy with this? How are you feeling about this, Tamara? Better, right? So this is a much more reasonable distribution than what we had seen before, right? So feeling pretty good about this. So what I'm going to do is I'm going to go through and I'm going to plot this out, right? So I'm just going to go through and steal my explore syntax, paste this, and then paste in my natural log of my role functioning variable here. Okay. Just run that. Yikes. Chrissy, what am I seeing in my graph here? Can you unmute? There you go.
I think the spacebar thing only works like half the time.
you gotta really punch it down.
I think the spacebar, you have to press back into Zoom to do it.
Oh.
Okay. So if I'm looking at my own stuff.
Yeah. Thank you,
That
Tamara.
might be true. So it doesn't look great.
Yeah.
So you still have a bunch of zeros and non-zeros.
Yeah.
And it doesn't look a ton better, but I guess the values are better.
Yeah. So what we've done here is we've gone through, and remember that our transforms, they're not magical, right? If I only have 5 values in my raw variable, and I take the log transform of those 5 values, how many values do I still have? 5, right? So it doesn't do anything, right? In terms of changing up, it doesn't turn it into a continuous variable. But what it does is it starts to bring this in, right? And so those values that were way out start to come back farther in. And so it does improve the distribution, right? it makes the skew less because we're bringing values in, and it makes it much less peaked than it was before. But at the end of the day, we're still working with a categorical, an ordered categorical variable, right? Transforming didn't change that. It brought it more in line. But if we see like our histogram and our box plot is still showing the first quartile, third quartile, and the median all is 0, and then everything else kind of hanging up here, right? So is what we did helpful? It definitely made things better in terms of just the numbers than it was before, but we didn't fix the fact that what we've done is inadvertently selected an ordered categorical variable as our outcome, right? And so at this point, well, even before we got to this point, we should be thinking about a different model. What we're going to do instead is pretend that this is fine, or at least acceptable, and move forward. But what you'll see as we start to move through our residuals is a lot of kind of weird stuff that comes up because the level of measurement of our outcome variable isn't technically, or not, is just not appropriate for this type of model. Okay. Questions on what we've done up to this point? People feeling okay with this? Okay. So what we want to do now, so we've got at least something that we're going to say is at least kind of acceptable in terms of our distributions. What I want to do now is I want to go through and take a look at my Z-scores. Sally, what am I looking for in Z-scores?
Values that are outliers.
Yep. So I'm looking for extreme values, right? So I'm going to say looking for extreme values. Okay. So I just stole my descriptives command here. I'm going to get rid of save because I don't need to save Z-scores on Z-scores. And I don't need to get skew and kurtosis of my Z-scores because that's going to be same as skew and kurtosis for my residuals, or excuse me, of my original variables. But what SPSS does is it just adds a capital Z to the front of the variable name. So I can say I want Z-scores of pain. We don't need to worry about opiate use here. Get rid of that. Z-score of PTSD, and then Z-score of LN roll. Okay. People see what I did to modify that syntax? Okay. Yep. And so all we're doing is just going to look at our descriptive statistics, and what we're really interested in is our min-max values for Z-scores for variables going into our model. Okay. So we go through here. Ignacio, what are we seeing in terms of potential extreme values here?
Well, we have following the criterion of the class. We don't have any Z value that is less than or bigger than 2.29.
Yeah.
So probably the base severity could be close or even PTSD, but they don't exist.
Yeah. Okay. Yeah, I'm having a little bit trouble hearing your sound, but I think you're on the right track. You're on the right track. If we go through and we see, again, remember looking at both the min and the max, right? Our largest Z value is 3.04, right? So for our PTSD score, we have someone who's a little over 3 standard deviations above the mean. But again, with 200 people in the sample, these values aren't enough for me to start become worried about extreme values, things like that, right? So in terms of extreme values, not too concerned about anything that's going on here, right? Being careful when you're writing this up, sort of making sure that you're indicating what you're identifying as extreme values. But if we're using a p equals 0.001, that 3.29 portion is kind of what we might say is, oh, that's starting to get beyond something bad. You know, some people will say 3, some people will say 3.3. again, it's a rule of thumb. The differences are likely trivial, but for these data, not looking like there's anything here that we need to be concerned about. Okay. Questions about this? All right, cool. So this takes us through a lot of what we have covered already up in this semester in terms of looking at distributions, looking at outlier or extreme values and things like that. What we're going to do now is we're going to go to our data and we're going to request a scatter plot. We're going to look at the bivariate relations between our variables, and this starts to become important. CJ, what are we looking for in? Because what I'm going to do is I'm going to request bivariate plots. What am I hoping to see in terms of my bivariate plots in this screening?
I think we're looking to see homoscedasticity
Mm-hmm.
and linearity.
Yeah, exactly. What we want to make sure, remember that because we're always going to violate that fixed effects assumption of our regression models, right? We're not collecting fixed predictors. We're almost always collecting random predictors. And so because of that, we've got a violation of our basic model. But that violation doesn't confer bias into our results so long as our data are multivariate normal, right? And we're going to assume that our data is multivariate normal. Multivariate normality is a difficult thing to check, but we're going to assume things are reasonably approximating or not too far off of multivariate normal if, one, my univariate distributions are all relatively normal, and two, bivariate relations between all of my variables are linear and homoscedastic, meaning that there's no weird nonlinearities and that the variability across the range of x relative to y is all sort of pretty much the same. Okay. So what we're going to do is we're going to go up to graphs. I'm going to go to chart builder. And then I'm going to go down and I'm going to click scatter dot. And then you got this matrix right here. I'm going to pull this up. And what I'm going to do is I'm going to start loading this with my variables. So what I'm going to do is I'm going to start with natural log of roll functioning. I'm going to pull that in. And then I'm going to go pane, drop that, PTSD, drop that. And then I didn't do this in the handout, but I'm going to go through and I'm going to enter opiate use in there as well. And I'm going to drop that down in. Okay. Then I'm going to hit paste. And what I've got here is a big, massive syntax command. I'm going to go through and I'm going to run this. And this is going to give me sort of my output. Okay. Now we're going to do some stuff in SPSS to try and make this a little bit more user-friendly. All right. Is everybody to this point? So to speak up if you haven't gotten to this point.
Which plot did we use? My SPSS isn't working.
Okay. So yeah, we went to graph to chart builder, and we went to scatter dot, and then this matrix plot right here.
Okay.
You got it? Okay, cool. Okay, so what we're going to do, if this is up in your window, if we double click this, it's going to open up a window that gives us a little bit so we can start to play around with this. And if I double click on the plot here and I go to chart size, I'm going to increase the size of this so it's just a little bit bigger. 460 for me increases it to be big enough so the whole thing still fits on my laptop. So just in the height, type in 460 and hit apply. And that's going to make everything a little bit bigger. That sort of expands things out, which I like. Okay. Then what I'm going to do, so I'm going to click out of this. And then I'm going to go to individual value here. I'm going to double click on that. So what it's given me is an open circle. I don't like open circle. So what I'm going to do is I'm going to make this smaller. And I'm going to fill this in with red because I just kind of like it. And that's going to give me a little red dot with a black ring around it. I'm going to hit apply. All right, and that makes those dots a little bit easier to see. Okay, so I'm going to close this. Then what I'm going to do is I'm going to go to Elements. I'm going to click on Elements. I'm going to hit Fit Line at Total. Okay, what this is going to do is it's going to give me a options to create a line here. I'm just going to leave linear, so this is just giving me basically a regression of my sort of linear function for each one of these, just so I have kind of a reference there. So I'm going to hit close now. So we've got a linear line there. And then I'm going to go to Options, and we go down to Show Charts and Diagonal. And if I click on that, what it's going to do is it's going to, in the diagonal here, it's going to give me my histograms for each one of my variables, which is going to help me. It's just a nice reference. If we get weird stuff in our bivariate plots, it's often because we have weird distributions, univariate distributions, and so this kind of helps me out here. So I'm going to close this, and then get out of here thing. And then I'm going to close out of this. And what I've got now is a bigger plot that's a little bit easier to see things going on. Okay. And so what I'm looking for here is I'm looking for clear evidence of nonlinearity, and I'm looking for problems with heteroscedasticity. So, Sean, are we seeing any big concerns in this plot here? No, you're on mute.
I mean, I don't really see any heteroscedasticity. Their pattern looks pretty much equal above and below the line. It doesn't seem to either cone out or in or out.
Yeah. Any problems with nonlinearity in these data?
I don't see anything.
Yeah. These data are probably looking okay. All right. What we want to do is we want to see strange issues with nonlinearity, right? So we want, if you're looking at me in my video, remember what we're looking for is weird stuff where we've got clear non-linear relations in my data, right? So exponential types of functions or U functions. If I go through in our screening, let me see if we, stuff like this, right? That would suggest some type of nonlinearity. Other strange things that aren't consistent with a linear relation, right? So if you were to look at these data and saw something that started down here and then like skyrocketed up, looked like it was a curvilinear function, then you might be concerned that you don't have a linear relation between your two data, between your sets or between your data, and that might be concerning. Okay, but we're not seeing anything over here looking too bad in terms of nonlinearity. And then the other thing too is we're wanting to take a look at homoscedasticity. And remember that what we're thinking about in terms of homoscedasticity is something where we're seeing the smallest to the largest spread increasing by a factor of like 3. So if I'm looking at right here, let's say the relation between my natural log of roll functioning and my PTSD score here, it looks like as my natural log of roll functioning increases, variability in my total PTSD score decreases. Okay, so that's something maybe I want to take a closer look at because we're seeing kind of that reducing shape here. Do people kind of see why this might start to look like a heteroscedastic relation? Okay, so we might sort of flag this as something we might want to look into a little bit more. The other thing I did is I requested my dichotomous variable to be included in this plot. This is a varying utility, but basically what we can do is we want to see if we look at opiate use, 0, 1, right? This is 0, this is 1, this is no people who are using. What we would want to see is make sure that we just don't have a lot of variability for one group and not a lot of variability in the other group. What have we called greater variability in one group than the other group last semester? Anybody remember? Chris M?
Don't recall off the top of my head.
What do we say when we have different variability across our groups? What do we call that when we're screening for like t-tests and ANOVA and things? Anybody ready? Chris C?
It doesn't have homogeneity of variance.
Yeah. So we got a violation of homogeneity of variance, right? So basically, our homoscedasticity assumption is functionally the same thing as homogeneity of variance, just with our continuous predictors. It's not more variability in one group than another. It's just variability across the whole thing. So it's not anything that's super new. But if I'm going through and I'm looking at variability in my continuous predictors here along this side relative to use and non-use, Alicia, am I seeing anything that looks like a whole lot different variability in one group versus the other based on the scatter of this? No, it doesn't look too bad. Okay, so this plot is looking all right, but what I might want to do is, let's say that I was looking at this graph and I see one panel here that I might want to take a little bit closer look at. What I can do, I can go to Graphs, and go to Chart Builder, and let's say now, so I'm going to go Scatter, but this time I'm just going to take my bivariate plot here, and the panel I'm concerned about looks like we have roll functioning or natural log of roll functioning on the x-axis and PTSD on the y-axis. PTSD on the y-axis. Okay, so then I'm going to paste this. If I go through and I run my syntax for that. Okay, and here's my plot here. So if I double click and change my point size, 3 fill, apply there. Yeah. So I go through and take a look. So we can see here up close, as roll functioning increases, it looks like I do get a general decrease in the variability of my PTSD total score. But Nick, is this something that's probably reaching the level that we might have serious concerns about?
I would say not quite reaching that level.
Yeah, it looks like at the high end of roll functioning, my variability is about half what it is at the low end. And this kind of makes some sense, right? At low levels of roll functioning, I got a whole range, PTSD going from nothing to super high. By the time I get people who are higher in PTSD, reporting the highest maximum level of roll functioning, their PTSD scores are sort of a much smaller range, which makes some sense. We would expect people at the highest range of functioning not to have massively huge PTSD scores. So this makes sense given what we've measured. But again, it's not, this variability isn't, or the range here isn't about more than 3 times what we've got here. So we're probably not too concerned. Okay. So up to this point, what we've done is we've gone through and we've taken a look at our univariate distribution. We've looked at missingness. We've looked at plausibility. We looked at our distributions, and our distributions were good for our predictors. Our dichotomous variable has a relatively equal split, and our pain and our PTSD variables have reasonable distributions, but we did find a problem with our roll functioning variable. Turns out roll functioning, as we've measured, it isn't continuous. It's ordered categorical, which is problematic. And then not only is it ordered categorical, it's also heavily skewed, with the predominant with far more people reporting 0. So we've got a basic concern with whether or not these data are even appropriate for linear regression. The answer is no. There are better models that we could use to analyze this. But because regression is our tool, we went through, applied a transform. That did a nice job of kind of brought it more in line. Doesn't fix it, but it's sort of better. Okay. And so then went through, and once we've transformed, doesn't look like we have extreme scores that we're going to be too concerned about. Our bivariate plots look to be fairly reasonable, although we'll see that it's these variables that have or there's associations with role functioning are the ones that are looking like we have some degree of heteroscedasticity, but not anything that's going to be bad enough for us to be concerned about. Variability across my opiate groups and non-opiate groups look to be okay. So really, to this point, our biggest concern is that with the level of measurement of our outcome variable. But we'll sort of make the best of what we've got with this. Okay. Questions, anybody, on anything that we've covered up to this point? Feeling comfortable with this at least? Okay, cool. So what I've heard is that following courses on Zoom seems to be more taxing than being there up front and in person. Let's take a quick 5-minute break, and what we'll do is we'll jump back in with our residual analyses when people get back. So try and keep it to 5 minutes and then jump back in, and we'll pick things back up. All right, cool. So I'm going to pop back into our output. Okay, so everybody feeling good about where we're at up to this point? Good. Okay, cool. Yes. So what we're going to do now is we're going to start and we're going to take a look at our residual output here. So in SPSS, what we can do is we're going to go to Analyze, and we're going to go to Regression. We're going to go down to Linear, okay? And we're going to actually run the regression model that would eventually want to run through and analyze. So we're going to take the natural log of role functioning, put that into our dependent variable, and then we're going to go through and let's put in opiate use, pain, and PTSD as our explanatory variables here. Okay. Then what we're going to do is we're going to go up to statistics, and we're going to ask for collinearity diagnostics. And you can check part and partial correlations. We'll eventually get to that eventually. You can click case-wise diagnostics. That'll give you some output it's kind of a summary output, so you can click that. And then hit continue. And then in plots, we're going to ask for some residual plots. And so what I'm going to do is I'm going to go through and ask for, we're going to put our predicted values, our Z predicted. So this is going to be our standardized predicted values. This is going to be our Y hat, our expected value of our outcome based on our model. We're going to take Z pred and put that into the X field. And then my standardized residuals, I'm going to put that in the Y. Okay, and what this is going to do is it's going to give us our regression or our residual plot here. Okay, then I'm going to go and ask for my standardized residual plots. I'm going to ask for a histogram and a normal probability plot. Okay, I'm going to hit continue. So in SPSS, this is going to give me some plots that we're going to go then through to use to take a look at our residual diagnostic stuff. And then what I'm going to do is, yep.
Quick question.
Yeah.
On the handout, when you're doing the plots, you have the Z pred by the SD residual.
Oh, yeah. Okay. Yeah, let's go back to plots. Thank you. It really doesn't matter for this plot, but yeah, the SD residual, that's your studentized deleted residual. We can go through and put that in. So yeah, let's do that just so that we're consistent with what I had on the handout. It shouldn't change things a whole lot, but we can go through and do that. Thank you, Alicia, for catching that. Okay. All right, so we're going to hit continue. And then under save, what we're going to tell SPSS to do is, as it runs this model, what it wants to do, what we want it to do is save some different output. And so we want it to save our studentized deleted residual, my cooks, which is my measure of influence, and then my leverage values, that's my measure of leverage. Okay, so this is going to be our discrepancy measure, our studentized deleted residuals. This is going to tell me whether or not I have weird things going on in Y space. These are going to be really sort of big residual values cases that we were way off in terms of our prediction, right? Our leverage, this is going to be our multivariate outliers, or our weirdness in combination of our predictors. And then Cook's is going to give me my measure of influence. Okay. Any questions on what we've requested here? There's lots of other statistics we could ask for, but we'll have plenty on our hands with this. So I'm just going to go ahead and I'm going to hit continue. And options, no, okay. And then I'm going to hit paste. All right, so here what we've done is we have our regression model. But we're not going to run this regression to look at our coefficients. We're going to run this just to get our residual output and things like that that we'll go through and evaluate. So I'm going to go through and I'm going to run this. All right, and this is going to give me my output here. So we're going to go through and see that I've got output for a regression model that I would normally go through and take a look at individual scores. This is your diagnostics, some different residuals and things like that that you could go back through, kind of summarize some of the things we're going to look at. But the first thing that I'm going to go down through and I'm going to take a look at is going to be my residual plot. Now there's going to be a couple things that I'm going to do with this residual plot to increase kind of the interpretability of it. Again, so I'm going to double click on this and that bring that up. So I'm going to blow up the chart size. So I'm going to say bring that up to 460. Okay, and hit apply. And then I'm going to go through and change my dots again, just because I like these better, and hit apply. Okay, and then I'm going to go through, I'm going to go to options, and I'm going to say y-axis reference line. So if we go through and hit that, what it's going to say is it's going to position this y-axis, this reference line at y equals to 0. And so I'm going to, okay, we got that. And so I'm going to close that. And so now we've got a reference line equal to 0. What's special about a reference line equal to 0, Chris C?
That's a 0 Z-score. That's like the ones we got dead right.
Yep. That's going to be the ones that we're right on. And remember that by definition, the mean of my residuals in OLS regression is going to be 0. The average score or residual score is going to be equal to 0. And what we're looking for is linearity, normality, and heteroscedasticity in our residuals. So this midline gives me a nice reference for I should have equal distribution above and below this. Okay. And then what I'm going to do is I'm going to go to elements, and I'm going to hit fit line at total. But this time I'm not going to ask for a linear plot. I'm going to click this lowest. And what lowest is giving me is it's giving me a smoothed function that's kind of the best fit for this line. Okay. So I'm going to click lowest, and I'm going to unclick attach label to line because I don't want to have that function on there. And I'm going to hit apply. Okay. And then I'm going to close. I'm going to close. Okay. So what we see is this is our residual plot. This is our standardized predicted values for all of our cases. So this is our standardized, our z-score for our expected value of y, plotted against our studentized deleted residual. Can someone remember, anyone recall what our studentized deleted residual is? Don't be shy. Just give it a shot. Anybody brave? Go for it, Sean.
Is it a residual that's standardized by the standard deviation?
Yep, it is kind of. When we're talking about, so yeah, but yeah, it is a standardized residual. What's the deleted piece of it? Do you remember?
Is it like what the regression would be with or without the value or something like that?
Close. Nice work. So what we've done is remember that if we go through and we were to take a look at our plots here, okay? And panel B here is what's maybe good to look at. So if we take a look at panel B, we see tomorrow for this point, when we're running a regression line with all 5 data points, what's the residual for this data point here? Is it big or is it small? Big. Well, if this dark line is the regression line with all 5, it's going to be really small, right? And so if we were to just look at the standardized residual for this case, it would be associated with a small standardized residual, okay? But if we run this model without this data point in there, Chris, see what happens to my regression line if I exclude this from the model?
It's probably a much better fit.
Yeah, it's a much better fit, and our regression line is now here. And if we were to look at what the expected value for this case would be when it's not in the model, it's going to be here. And so what would the residual be if we were to run this model without that case in there, and then looked at the expected value for that case versus what that case actually got? Now all of a sudden we've got a pretty big residual here, right? People seeing that? And this is what our studentized deleted residual gives us. It says if we exclude this case from the set and we run our regression line, what's the difference between that case and what that case would register, should register if it in the model without that, right? So it's a little bit, basically what it's getting at, it's a much better, our studentized deleted residual is a much better indicator of kind of getting at some of that influence, right? So how far away would this score be from the actual predicted value if we're not sort of in there? So this is where our standardized residuals can start to mask a certain problematic values, because when this value is in there, boy, it looks pretty good, but it's only looking good because it's drugged that regression line all the way down and changed things quite a bit. Okay, people see what's going on with these studentized deleted residuals and why they're useful? Okay, cool. So that's what we have here. We have our our predicted values, standardized predicted values against our standardized deleted residuals. Here's our midline. We should see, again, everything looking, if we've got a good residual distribution, it should look something like this. Here's my midline, here's my 0. I'm seeing everything kind of scattered above, below, and everything's looking pretty fantastic here, okay? Is this what we're seeing? No, Chris M, tell me what's going on, or tell me what we're seeing here.
It's skewed pretty dramatically because of the nature of the variables themselves.
Yeah. What we've got, instead of a nice clean cloud, we've kind of got a mess where we've got this line, this line, this line, and this line, and this line, right? It's not a big, nice cloud. And we've got problems with maybe sort of the distribution here. We've got a huge skewed distribution because here's where all of our values are clustered up. And when we miss, they're way above, right? Miss, they're way above. So these are values, standardized residual values. These are expected value, or these are observed values that are way above what we would expect them to be, right? And so as we go, so we have a lot of skew, and then kind of things kind of skew off here. My lowest line, this is a continuous measure of fit, so it's going down, following sort of this very straight line of residuals here until we get to this point, and then now all of a sudden we got more residual stuff up here, so it's kind of coming up. So it's giving me a weird kind of line. So again, we're looking at this residual plot for concerns with, we're looking at issues of normality, linearity, and heteroscedasticity. Okay. Do we have a problem with linearity here? probably not, right? It's hard to tell because it's this weird stuff going on with these data. Remember that because we only have 5 actual outcomes, right? That's going on here, 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 and here. So we only have 5 possible observed values for my outcome, which is causing these striations here. But I'm not seeing anything that looks wildly non-linear, at least in sort of a systematic way. It's hard to tell, but it's just kind of an ugly plot here, okay? But I do probably have some concerns with the normality of residuals, right? If I go through and I take a look here, this is what's going to, like, if I've got skew, I've got everything kind of set up on this midline, and then when I miss, they're constantly missing low on this graph, right? If I go up and take a look at here, like all of my values are kind of up here, and then all my residuals are kind of getting skewed up here, which starts to look kind of problematic, right? So I might have some concerns there. And then homoscedasticity is really hard to tell, right? So really, my variability is kind of equal in that it's all kind of the same from my highest to my lowest until I get out here. And then there's really no variability because I've just got individual points. And then here, individual points, right? So it really makes it kind of hard to get a sense for whether or not I have properties of homoscedasticity. Again, heteroscedastic residuals might look something like this, right? These are all normally distributed, right? At every single value of my predicted or my expected outcome, the variability is all equally normal above and below. But here I have very little variability. Here I have a whole lot of variability. Kind of hard to see, but it looks like heteroscedasticity or homoscedasticity might be okay here, but it's just, again, what we've done is we've regressed a variable that shouldn't be regressed onto something in a standard regression model, and what it's doing is it's causing some difficulties in interpreting this. Okay. Questions about this plot, about how what we're looking for within these residual plots? Okay. Yeah.
So the lowest line is some kind of regression, right?
Yeah.
It just says that a non-linear approximation of the base fit of the data.
Yeah, here. Watch this, Ignacio. So if I go to Chart Builder and I sort of, okay, yeah, we'll just use this. All right, so this is my association between the natural log of roll function and PTSD. If I hit this, right, and then I go through and I go elements, fit line at total, lowest. Okay.
Right.
Well, I'm not sure why it didn't. All right, here, let's do this. I go Analyze, Graphs, Chart Builder. Instead of PTSD, let's do Pain. This will be good. Okay, so Elements, Fit Line, Lowest.
I got it. So we don't use the lowest line instead of the regression line because it would be very hard to have an equation that could be useful to us, right?
Yeah. And so what the lowest line is doing is, because if I've got something like this where a bunch of plots are kind of all stacked up on one another, or imagine this, let's say we had a case where we had, say, 5,000 data points. What we might get is a really thick cloud that looks kind of uniform across it, but what's actually happening is there's a bunch of cases all kind of on top of one another in kind of a curvilinear shape. What this lowest line will go through, and it's going to say, oh, well, this is kind of where the majority of cases are going through. So what I think is nice about this lowest line is we can kind of use it to see, do we have evidence of nonlinearity that could be difficult to see graphically? And so this plots it out. And so here we're seeing that, yeah, even though this is kind of all spread out, you see kind of minor deviations, but it's just it's fitting the data. It's not something that's going to be generalizable to any sort of actual phenomenon, but it's just kind of fitting that. It just looks friggin' weird when we do this because of the nature of those data.
Hey Josh.
Yeah.
Does that residual plot suggest that there are some group level effects? So it looks like just the intercept is just changing in the 5 different categories.
Yeah. I mean, basically what we've done is we've got a screwy outcome. And if you do that, it's going to give you, so the vast majority of people scored 0 on functioning, right? And so some of these people here, these are people who we overestimated values, underestimated values. This is just people who have a value of 0 on their functioning scale. These are people who had originally 25, 50, 75, and 100. They're just all kind of lining up there. And so, again, this is what happens if you're trying to run diagnostics when your variables don't fit with the model that you're trying to run. So we should be using a different model. Okay. So, but if we're going through and we're taking a look, we say we've got some screwy stuff. But one, it doesn't look like there's problems with with nonlinearity, at least obvious nonlinearities. 2, my variability, I don't know that I would make strong claims on violation of homoscedasticity because the range of scores is functionally identical until we get out here where we just don't have that many people to go through and actually kind of take a look. But then we may maybe we have some concerns about the normality of our residuals, right? And so what we can do then is go down, move up, and take a look at a couple different histogram or plots of our that are going to tell us whether or not our residuals are normal. Okay, here we've got our PP plot, our cumulative probability plot. Chris C thinks that's funny. People like it. But again, Chris C, what should we see on our PP plot if our data, whatever we're modeling, is generally normal?
It should just kind of line right up with that diagonal line there.
Mm-hmm. The idea, I like that. It's like you're dabbing. That's good. This is just capitalizing on the human eye's ability to follow kind of this diagonal line. And so we can start to see that if we see deviations from this, it's indicating some level of non-normality. Here, we've got some deviations, but it's not too bad. So normality of our residuals is looking okay. If we go up and take a look at our histogram with a normal plot superimposed, we see that it's, again, maybe some positive skew here. We've got a nice normal distribution, and then here at the end we've got another thing going on, right? And so this is speaking maybe back to Sean's concern that maybe we have some grouping effects. We have people who are reporting 0 level of functioning, and then people who are kind of reporting some level of functioning. We've kind of got, like, we might hypothesize we're working with 2 different populations. Here's the first one, and then here's the second one, and we've just kind of butted them up together. Our regression model isn't a good way to go through and test that out, but in terms of generally what we've got going on, we say, okay, well, we don't have clear evidence that these residuals are wildly off base. Okay, so in terms of our in terms of our residual plot, we'd say we've got a funky plot just because our outcome variable is questionable. But in terms of clear evidence of nonlinearity, non-normality and heteroscedasticity is not looking like we have clear evidence that we have something that we need to be concerned about. Okay. Questions?
Last question.
Yes.
Why don't we use as a reference Shapiro-Wilk or Kolmogorov, Smirnov or those?
I'm sorry, I can't hear you, Ignacio. Can you speak up, or what did you say?
Sure. Why don't we use? What is the problem with the test like the Shapiro-Wilk or the Kolmogorov Smirnov test for normality? Why don't we use them?
Yeah, why don't we use normality tests? Why aren't we interested in those? Anybody? So what's that?
Some variables are non-normally distributed.
Okay, so some variables are going to be non-normally distributed, so we would expect them to violate normality, right? But if I run a significance test on normality, what is that asking? What is that a test of?
Whether or not... Wait, hold on. It's like whether or not the data is not normal.
Yeah. And not normal is in sort of equal to what?
Oh, zero.
Yeah. Do we assume that our distribution has zero skew or kurtosis? No.
No, we're assuming that it just has reasonable.
Right. And if we have really large samples, like we should for running regression models and things like that, how's that going to power that statistical test?
It's going to make it really easy to not be zero.
Right. And so, Ignacio, this is what ends up happening. People get excited about Shapiro-Wilk and some of these other normality tests, but it's really, they're not. I would make an argument that they're not terribly useful, because for my assumptions, the assumption of my test isn't that the skew is zero, right? It's just that it's not bad enough to start causing problems. And particularly if I have really large samples, what those tests will start to do is pick up Annie's tiny deviation from zero. And so what will happen is people will start to report that they have non-normal data based on a significant Shapiro-Wilk, something like that, and then starting implementing transforms and things like that aren't necessary and incredibly complicate their test or their interpretations, because basically what those tests are asking is the skew of these data different than zero, even if it's a little bit, right? And so when I'm reviewing papers and people will say, oh, we have non-normality, I'm like, okay, well, what was that normality? It'll be a skew value of 0.25 or something like that. You don't need to transform any. Is it zero? No, it looks like it's probably not zero, but it's not something that we need to start doing a bunch of stuff to the data for. Does that help?
Yeah.
Okay, cool.
Thank you.
Other questions about what we're looking for in this residual plot, or some of the other stuff? Okay, so what we're going to say is that for these data, we're probably not going to have huge concerns. Well, I mean, we do, just because the outcome variable looks screwy. But in terms of outside of our dependent variable being screwy, we're not going to be too concerned, probably, at least, or sound the alarm in terms of non-normality, non-linearity, non-normality, or heteroscedasticity here. Okay. All right. So next thing we're going to do is I want to look at my discrepancies. Okay. Who do I want to pick on? Nick, can you tell me what we're looking at in terms of our discrepancies?
So this is like the magnitude of the difference between our observed and our expected values in terms of the residuals.
Perfect. And what I'm going to do, is I'm going to go to Analyze. Oh, and I should have mentioned this. So if we go through and we take a look at our data, right, we'll see here at the end of the file, we've got our studentized deleted residuals, our Cook's values, and our leverages here. And what SPSS did is it went through and it wrote for each individual. I've got a studentized deleted residual, I've got a Cook's, and I've got a leverage. Okay. So what I'm going to do is I'm going to go to Analyze, Descriptives, and then I'm going to ask for, give me the descriptives for my studentized deleted residual. I don't need to save standardized values. I don't need skew and kurtosis here. All right, so I'm just going to paste that. Okay, so go through, take a look at my discrepancies. If I run this, okay, and Nick, keep going. Tell me what am I seeing here in terms of my studentized deleted residuals?
So we don't see, I mean, the max value is getting close to 3, but that's not the most important thing to pay attention to. They follow a t-distribution, so there's some formula, I can't remember what it is, that we can use to kind of compare and see if it violates that, if there's any problematic values, but this looks like that's probably not the case. Yeah.
So again, for the formula that Nick is referring to is our studentized t residuals. They follow a t distribution with n minus p minus 2 degrees of freedom. And so if we wanted to, for any value in this case, we could identify a p-value for each one of these, right? Which we could, but again, we're not really interested in the p-value associated with that. But what's nice is we can start to, particularly in a large sample, we can start to interpret these kind of roughly around the same guidelines as we would with our Z statistics, right? So if we get values and sort of treating these kind of the same way as we might treat like extreme scores with our Z-scores. So if we had a studentized deleted residual of like 4 or something like that, or 5 or something huge, that might suggest that we've got a case similar to something like this, right? But we've got a large sample, and we're expecting some to miss on some cases. So generally, Nick, again, are we too concerned about the magnitude of the minimum and maximum values for my discrepancies here?
Nope.
Probably not. Nothing too bad, right? But what we do want to do is go through and plot these out to see what the actual distribution looks like. So if we go through, and I'm going to hijack my examine, right, because I'm going to go through and create some plots. Do this. Okay. And so I'm just going to go through and I just want to get plots of my studentized deleted residuals. Alicia, what am I seeing in this distribution?
A little bit of positive skew.
A little bit of positive skew. But anything that's looking like it's way out of bounds or anything I should be too concerned about?
No.
Okay. Same thing, Ignacio, with this box plot. Is there anything that looks like it's way out of bounds or something I should be concerned with?
I wouldn't say no. They appear to be a couple of those, like 5, 6 extreme values, but no.
Yeah.
Actually, no.
Yep. This is looking pretty good, right? So we've got some high, some large residuals. We've got some smaller residuals, right? So we've overestimated things in some cases and underestimated things in others. But the reason why is we're going through and doing this. In the lecture slides, I gave you some rules of thumb to interpret some stuff, but that's not the end-all be-all of this stuff. Okay, what you really need to be looking at, cases that I'm going to be concerned about are ones that are way out here, that fall way outside the rest of the distribution. Really funky cases that are very clear oddballs. We might say, well, and even this isn't too bad. We might say, sort of scores above 3 or 3.3 or 3.29 or something like that might be worth sort of noting. Here, there's really not anything even to be too concerned about. What we'd be looking for here, case number 269 is high in terms of our studentized deleted residuals, but we're looking for stuff that's way, way out of bounds with stuff. Okay, so for our discrepancies, nothing too much to be worried about here. Okay, Questions, anybody, about discrepancies or how we went through and looked at that? Okay, cool. Next thing we're going to do then is we're going to go through and we're going to take a look at our leverages. What else do we call leverages? Chris M?
The difference between your expected value and the
Okay, so our discrepancies, this is looking at stuff in Y space. So here we're looking at expected values versus other stuff. Do you remember what we're looking for with our leverages?
I can help.
Okay. Jump in there, Alicia.
Multivariate outliers.
Multivariate outliers, right? Here we're with our leverages, this is looking at stuff in X space. Okay. Discrepancies is Y space. What's the difference between our expected value and what we actually observed for this case? Leverages is going to look on the opposite direction. Do we have weird combinations of predictors that don't make a lot of sense given what we know about the data? So we'll say leverages, and these will often would generally refer to as multivariate outliers. And so if I go LEV1, right, what this is going to do, give me an opportunity to look at some of these leverage cases here. Okay, so if I go through and I take a look at my descriptives for my leverages. Now remember that for our leverages, what we're looking at in terms of things that we might want to start taking a look at. Now remember that SPSS calculates leverages as differently than Stata does. SPSS calculates centered leverages that range from 0 to 1 minus 1 over n. And so what we're looking at in terms of benchmarks, things that we might want to go through and look further into in terms of cases that may represent multivariate outliers, is I'm going to say things that are 3 times the number of predictors over n. So in this case, we've got 3 predictors. So we take 3 times 3, so that's 9 divided by 201, gives us kind of a general threshold for further investigation, anything that's 0.045 and above, okay, for my centered leverages. And if I look at my maximum value for my leverages, Sean, does it look like I might have cases that might be big?
There's one.
What's that?
There's at least one.
There's at least one, right? So what I'm going to do is I'm going to go to my output, and I'm going to sort ascending for my leverages. I don't care about small leverages. But again, if my cut value or threshold is 0.045, it looks like I've got about 5 cases that are registering largish leverage values. Okay, now this starts to become important. These are just general rules of thumb for things that are ish kind of large, right? If we get nuts and start just cutting off cases that incrementally eke above some arbitrary value, we're going to be in bad shape. Okay. Sean, is a value of leverage value of 0.045 different than 0.047 categorically?
They're pretty close.
Yeah, they're pretty close, right? And so this is the problem we have if we just set arbitrary guidelines, right? So we know that we've got maybe a collection of cases that could have weird combinations of X values in some space, right? But what I want to do before I get too nuts is go through and I want to graph these out to say, okay, what's the distribution? Am I seeing that one of these cases is really far above and beyond the rest, right? So if I go through and I run my leverages, okay. Now we're always going to see a skewed distribution with these leverages, but based on this output, is there any case, are there cases that are way above and beyond and like way out of bounds relative to the rest? What do you think, Tamara?
SPSS, like with the asterisk, I don't know the curl of that word,
Yeah.
but
Asterisks.
Yeah. But if we remove like those ones, then the ones next to them will become like
Yeah, exactly, right? And so we need to be careful because this can be an endless process. If I shave these guys off and rerun this, now all of these ones are going to be out there. And if I do that, and then the other ones are going to be down there, right? And so I want to be careful in what I'm identifying as a problematic value. So here it looks like case 310, 221, and 202 are probably my largest, my three largest values. But, yeah, they're big. But, Chrissy, am I seeing any of these that are like way out above and beyond the rest of stuff?
Just looking at the histogram distribution, it doesn't look like ridiculous or anything. It looks pretty close.
Yeah, right. And so when I'm looking at this, I'm saying, yeah, I've got some values that are kind of out there, right? But they look like they're generally kind of a continuous sort of following of the rest of the stuff. I'm not seeing huge gaps. At some point, we exceed values that are 1.5 times the inner quartile range, and then so my open circles turn into asterisks. But there are cases I probably want to take a closer look at, but not something. Again, I'm going to throw up the 5-bell alarm for. Oh, this is very clearly something that I'm concerned about. So our thresholds and our rules of thumb give us a nice guideline for context, but what we always want to do is take a look at the distributions and say, how far away are we from stuff? Okay. So Sean, Ignacio, for things that you guys are doing in marketing and sort of income and sort of money-based stuff, this is where some of these techniques can start to become helpful in identifying weird cases in your data. If someone's way, way out, if you've got a company that's making, $2 billion a year, and they employ 10 people and are spending, $100,000 on marketing a year, that's a weird configuration maybe that I might not expect. And that's someone who's going to be way the hell up here in terms of that value, or way out here on this, right? And that's going to be someone who's, hey, it looks like something about this company doesn't actually fit with the rest of them. It can happen in psychological science, and we want to take a look at it, but those are the types of things we're going to be most concerned about. Okay. Questions on what we're looking at in terms of our leverage values? Okay. Well, we do have maybe a couple of these cases that we might want to take a look at. Let's say we've got this cluster of three cases here on the end that are really in my histogram kind of set apart from the rest. They're values that are more than 1.5 times the inner quartile range, or 3 times the inner quartile range here. So let's say, just because we want to do it there, we want to go through and take a look at these cases. All right. It can be difficult sometimes to go through and figure out exactly what's going on with these cases. But if we're going to identify anybody as a multivariate outlier, I need to 100% always be able to describe what's causing that case to be weird in X space. Okay. So what I'm going to do is I'm going to go through and I'm going to create 3 variables. I'm going to say compute. I'm going to say MV1 equals 0. Okay. I'm going to copy that. Okay. So what I'm going to do, so I've identified these 3 cases, 310, 221, and 202 as cases that I want to explore further. Okay. So I'm going to say this is MV1, MV2, and MV3. Okay, people following me here? And what I'm going to do is I'm going to run this, and it's going to create 3 new variables at the end of my, I have to put periods after that. There we go. Okay. There we got them. MV1, MV2, and MV3. Okay, everybody got that? All right. And what I'm going to do is I'm going to sort my leverages. And then I'm going to go down, scroll down to the bottom of my data. And so here is case 310. This is my largest leverage value, right? So in MV1, I'm going to enter 1 for that case and nothing else. So case 310 has a value of 1 for MV1. Everybody else gets a 0. Same thing for MV2. I'm going to enter 1 for case 221 and see that. And then the same thing for MV3. Enter a 1 as a marker variable there for case 202. Okay. And so what I've done is with these 3 indicator variables, everybody gets a 0 except my one case that I'm interested in. Everybody gets a 0 except the case I'm interested. Everybody gets a 0 except the case I'm interested in here. Okay. And so what I can do now, and this is a trick out of Tabachik and Fidel, is I can go to Analyze, I can go to Regression, go Linear, and what I want for this first one is I'm going to enter Multivariate or MV1 as my dependent variable, and then I'm going to keep opiate use, pain, and PTSD as my predictors, right? Because there's something about this combination of scores that's weird. All right, so I'm going to go up to statistics, and I'm going to get rid of part and partial correlations, get rid of all this stuff, because I don't need this. I don't need any plots. Get rid of all that. I don't need to save any values, because I'm just going to be looking at coefficients here. Okay, so I'm going to go through, I'm going to paste. All right, I'm going to get rid of that scatter plot because it still wants to give me that. Okay. All right, and then I'm going to go back up here and steal this descriptives command. That's going to help me. Look here. I'm going to get rid of, because I don't want it to save variables, and I don't need Skew Kurtosis stuff here. Okay. So what I'm going to do is I'm going to run this regression model, regressing MV1 onto my 3 predictors, and then I'm also going to get descriptors for my predictors for my pain, opiate use, and PTSD. I don't need role functioning in there either. Okay. Okay. So what I've done is I've gone through and I've regressed MV1, that 0,1 variable, onto my 3 predictors. And if I look at what ends up predicting that one case, okay, this is not a variable that you would, or a model that you would run and try and present as much of anything, right? But for the purposes of identifying what predictor variables are creating our sort of weird combination is causing this case to be a multivariate outlier, or at least have a high leverage value, what I can do is I can look at my p-values here to identify what cases are really driving sort of that high leverage value. All right. And silently looking at this regression, this coefficient table, what variables look like they're contributing to this case? Oh, I think you need to unmute.
That is the pain severity
Mm-hmm.
and the PTSD that's the most.
Yeah. So basically, it looks like there's something about pain and something about PTSD scores for this case that are contributing to this being kind of a high leverage value. And if I look at the negative coefficient here, I'm guessing this is going to be a low pain score combined with maybe a high PTSD score in terms of something strange going on, right? And so if I go down through and I take a look at my descriptives, and I go through and I take a look at, for this case, this is someone who has the mean of pain is a value of 6. Okay. CJ, what's the pain score for case 310? 0.33, right? And the mean PTSD score is 50. What's the PTSD score for this person?
79.
Yeah. So based on these analyses, what's causing sort of the weird kind of the high leverage value looks to be a combination of very, very low pain and pretty high PTSD. Okay. And so for this case, given the sample, it seems like for this sample, people who tend to have that high of level of PTSD are also reporting pretty high levels of pain. This person is the exact opposite. They're reporting incredibly low levels of pain, 0.33. So this person is, if my standard deviation is 1.3, and this person has a pain score of 0.33, they're reporting pain that's several standard deviations below the sample mean. And then they're also reporting a PTSD score that's a little over a standard deviation above the mean in PTSD. And so for this individual, the weird combination of pain and PTSD, low pain and high PTSD, is what's getting this case registered as having a high leverage and is kind of creating what's starting to look like a potential multivariate outlier here. Okay. Questions on what we did, how we hijacked this regression model to further investigate this case that has what looks to be a reasonably high leverage score. People kind of see what we did and why we did it. Okay, cool. So we've got a couple other cases here that we wanted to take a look at. And this then ends up being pretty easy. If I just take my regression statement and copy it down and then just change that to MV2. Now I can just run this and see if I can determine what specific variables are causing this case to stand out. So we go down through and take a look here. Let's say, Chrissy, what am I seeing here in terms of something contributing to this having a large leverage value?
Looks like your PTSD total score.
PTSD total score, right? And so when we typically think of high leverage values, we tend to think about it being a combination of variables, but it doesn't have to be. Just having a high score in one area could be problematic, right? So if we take a look at our second case, Chris, what are we seeing in the PTSD score here?
It looks like the max.
It's the max, right? So what looks like is driving this person's high leverage value is just that they're at the very top end of PTSD, right? Now, was that case, Chris, do you remember, was that in terms of our Z-score, was that like a Z-score of 4 or 5?
I don't think we had anything that was that.
No, yeah, it's still around that 3 area. So it's high, but it's not that high. But it looks like this is primarily what's contributing to this case being flagged as a high leverage value. So I'm probably going to be less concerned about that individual case maybe than if it's something I have like just a really weird combination. Okay. And then if I do the same thing for the last case that I was interested in, because we're just going to investigate the highest 3 just from this. If I run that, Sean, what am I seeing here in terms of contributing to the high leverage value for this person?
Looks like the pain severity score.
Yeah, and what is it, high or low?
It's low.
Yeah. So for this person, we've got a pain score of 0. Okay, so they're at the very bottom. So again, in this sample, a pain score of 0 is not common, right? So the thing to remember when we're looking at our leverages, these, again, thinking about these in terms of things like multivariate outliers, what we're most concerned about are are weird combination of predictors that would suggest that the case is strange for some reason and not typical of the larger population, or it's representative of some subpopulation that's not well represented within our data, right? And so anytime we go through, one, thresholds are important. We want to say, okay, in general, is this something that would register as a large leverage value? But really, what we're looking at is things that are way out in the high mix. We've got some cases here that we might want to go through and sort of look into a little bit more. But honestly, here, there's probably not any of these that make me super concerned. What I might do is probably 310 is maybe that case with the high PTSD and the very low pain. What I might do is run this model with and without case number 310, see if it has a big impact on my results. And if it doesn't, I'm probably not going to be too concerned about it. Okay. But always what I would want to do first off, if I identify a case with a weird set of scores, want to go back through my original data, hard copy, make sure that it's not a transcription error, that sort of everything has been entered right, make sure that this isn't something that my RA or my research assistant has noted that the person like finished the whole thing in like 2 seconds or something along those lines. Try and identify methodologically, is there something going on? Are these accurate scores? And if they are, is this person someone who's, one, going to impact my model a whole lot, and then two, is someone who's representative of my target population? Anytime you're going to throw someone out of your research, you better do a good job of explaining why and give me a good reason why, because otherwise I'm going to think you just threw out people that didn't do act the way you wanted them to, right? But if you can say, this was a weird configuration of scores that doesn't make sense, really. This person didn't appear to take responses seriously or had some other characteristic. If I have this person in the data set, it completely changes my output or my results. Those are all good reasons to get rid of somebody. Questions on this? People kind of see how we've gone through. So again, the take-home message here is not just to identify that, yes, this case is a problem, then following up to say exactly what's causing this case to be a problem so that you can help understand your data a little bit better. That sound good? Okay, cool. Let's do this. Let's take another 5-minute break. People want to take another 5-minute break? Okay, let's take another 5-minute break. Be back in 5, and we'll finish up sort of working through this stuff. Awesome. Thanks, folks. All right. Cool. Let's jump back in, and we'll finish this stuff up. What?
Oh, we didn't learn that. We did centered.
Oh, there we go.
So I can't teach you Mahalanobis. Has Josh done in the lecture where he tries to talk to you about the different...
About the different what? I got kicked out. One of you guys kicked me out, and then I lost everything. What happened?
I was asking if you had talked to them about the different dimensions by using your fingers to...
Yeah. We can identify things in 3 dimensions. That's, you know what that is? That's 8th grade. That's 8th grade drafting class. Is what that is. All right.
I use my fingers to do this.
Yeah, right? X, Y, and Z. 3-dimensional space out here. Right? CJ's trying it. All right. Okay, cool. Let's go through. So we went through and we looked at discrepancies. Nothing really concerning there. Went through leverages, looking at univariate or multivariate outliers. One case that might be kind of a strange configuration, I'm guessing it's probably not going to have an impact on my outcome so much. The last thing that I might go through and take a look at is going to be my influence, right? And so what I'm going to do is going to basically do the same thing that I've done previously. I'm just going to steal that syntax. I'm going to go through, paste it out. I'm going to say influence. If I go through and my cooks is my influence value, so if I go COO, it's going to give me my influence. And CJ, what's my influence value, or what is influence giving me?
Let's see, influence isn't that a combination of leverage and discrepancy?
Yep, that's exactly what it is. Looking at a combination of leverage and discrepancy. And again, the idea is that these are going to be cases, so we can have cases that have high leverage values, and we can have cases that have. Was I frozen?
Yeah, you froze.
Okay, I've got a booster that's coming in today. Hopefully, will help this out. But so I've got if I can have cases with high leverage that really have no impact on my outcome or on my model. I can have high discrepancies with no real impact on my outcome. But when I start to get combinations of those, that can start to become problematic. And so my measure of influence is a combination of leverage and discrepancy to see, do I have cases giving me more evidence that a case might be problematic. So I'm going to go through, run my descriptives for Cook's distance. And again, recall that, again, my general threshold for Cook's distance is going to be cases that exceed 4 divided by n minus p minus 1. Okay, so for this set, I've got 4 divided by 201 minus 3 minus 1 gives me a threshold value of about 0.02. Okay, so if I go down through and I take a look here, CJ, do I have cases that exceed 0.02?
Let's see. It looks like, yeah, there's a 0.05 in there.
Yep. And so if I go through and I sort my cooks, and if what I'm looking for are cases that are exceeding 0.02, here I'm going to do this. I'm going to sort descending. Yeah, I've got 14. I got 14 different cases that are going to be considered high influence values. Okay, so again, do I want to just chop out 14 cases? No, I don't, right? And so this is why we need to be very, very careful and not just think, oh, I'm just going to use these rules of thumb to determine what my problematic cases are. So just like we did with leverages, I'm going to go through and I'm going to plot these. And if I'm going through and I'm taking a look, again, we expect a skewed distribution here, where most of them are going to be little, and then they're going to go out in the positive direction. But again, it's kind of like what I was seeing in my with my leverages. We got kind of just a slow drip continuation of things going out, and we've got cases that are very large, right? 130 is up here, 402. 185. So we've got a lot of stuff going on. So we've got cases that could potentially influence my results. But again, it's not looking like anything that I've got like way separate, like way different from the rest of my distribution, which makes me feel better. Okay. And so what I would say is that, yes, I do have 14 cases that are exceeding sort of traditional benchmarks for what would be considered high influence. I might take a look sort of this couple cases here, 130 and 402 look particularly large. And so I might make note of those. And what we should be doing is we're working through this is kind of trying to keep track of what are the cases that come up again and again. Basically, we're looking for bad penny cases that keep popping up again and again and again, and those are the ones we're probably going to be the most concerned about. If we've got a case that comes up as a univariate outlier and a high discrepancy value and a high leverage, and it continues to be weird, those are probably cases that we're going to be most interested in maybe addressing. Okay, so we've gone through and we've identified some leverage values that are kind of large, but things that I don't know if I'm super like panicked about. One of the things that's nice, and Stata does this better than SPSS, but we can use SPSS, is what we can start to do is start plotting combinations of leverage and discrepancies and things along those lines. And this can be really helpful in identifying cases that within the whole grand scheme of things start to get weird. So if I go to graphs and I go to chart builder, I'm going to request a scatter plot. But this time what I'm going to do is I'm going to take my leverage values and I'll put that on the x-axis. And I'm going to take my studentized deleted residuals and I'm going to put that on the y. Okay. And so I'm going to go ahead and actually reset. I don't know what happened there. Okay. So scatter here. I'm going to take my leverages, put my leverages on the x, studentized deleted residuals on the y, and then I'm going to paste. Okay. I'm going to identify this as lev by leverages by studentized residuals. If I go through and I run this graph, okay, and what I'm looking for with these, right? Again, Alicia, Stata will do a better job of doing some cool stuff. This is basically what I've just plotted here is a leverage by a studentized residual. What I've told Stata to do is make the size of these dots proportional to the size of my Cook's influence or my Cook's D, so I can see cases that are kind of bigger here, right? But I've got the same plot here, and so I can start to identify cases that are maybe strange within the context of my output. This is, I'm getting a plot that's looking, oh, okay, something strange. This is looking different than what your handout looks like. Looks like this older version of SPSS is doing something a little bit different. Don't worry about that for right now. But what I'm looking for here in this combination plots are going to be cases that are way up here in the upper right corner and the lower right hand corner. If on our x-axis we have centered leverages, these would be cases falling in this region are going to be cases with very high leverages and very negative studentized deleted residuals. If I get cases up here, these are going to be high leverages combined with very large studentized deleted residuals. And so those are going to be the cases where I'm most interested in sort of saying, oh, hey, this is a potentially problematic situation. Okay. Now, one of the things, it can be hard. So even if I do find a case that's potentially problematic in this scatter plot, it's hard to know what that case is, right? So what I'm going to do, what we can do is I'm just going to run this separately. And again, I'm going to double click on this. And if I go to elements and I clicked show data labels, okay, then I hit close and then close that down. What it's going to do is it's going to go through and it's going to label each one of these points with a tag so that I can go through and find sort of cases that I might be interested in. Now, the important thing to note, please recognize this, that these data labels, those aren't subject numbers, okay? These are case numbers. So case number, let's say case number 44. This is a case with a large leverage value, but has a pretty minimal studentized deleted residuals, not bad. But this is case number 44 in that this is the 44th case in my set. So this is actually case number 310. Okay. case number 40 or participant number 44, there's not even a 44 in here, right? Same thing. This is the first case in the set. First case in the set, right? But the thing is, if I go through and I sort this, and then I run this again, you go elements, show data labels. Now all of a sudden all my labels have changed because I reordered the people in reordered the stuff. Yeah, Chris.
Would it be possible to generate like an additional variable that takes the absolute value of your deleted residual plus your leverage value and just examine that to see if it reaches like 3.6 or something like that?
Yeah, I mean, so this is well, so I don't say that again. So you said the absolute value of your studentized deleted residual?
Yeah, if you're looking for people that are like in the extreme corners,
Mm-hmm.
if you have the individual values, can you just like add the two of them and make an absolute value one?
Well, what I would be concerned about is if you just add the two, if you have someone like this with a combination of a high leverage and a low studentized residual, and then someone with a high residual, and so the leverages are on different scales, it would probably be hard to interpret exactly what was going on, right? Okay. So there are different plots. Again, the nice thing about Stata is here we've got squared standardized residuals and leverages with lines indicating mean values. Here you'd be looking for something way up here. It's just hard. Like SPSS isn't set up to do this well. But what we can do is we can get the centered leverages by your studentized, look for these cases, and then we're just looking for cases that are going to be way out of bounds. So, Alicia, in this plot, is there anything that looks like it's going to be super concerning for our purposes?
No, I think number 19 gets maybe a little close, but nothing really overall.
Yeah, 19. But again, what we're looking for is stuff that looks way strange, right? Let me see. Oh no. Layla in her thesis was doing some screening and found like a case in this plot that was way out here. It was very, very strange. And so like that's generally the type of thing that we're going to be looking for. Okay. So again, a case with a weird combination of low pain, high PTSD, but our discrepancies look to be pretty good. Our influence levels, maybe one who's kind of a multivariate outlier, but probably not too bad. Influence, if we're just going by straight cutoffs, we got 14 cases that are problematic. But if we go through and we take a look, they're just kind of a continuous, they're not clearly set away from the end. And if we run our leverages by our studentized deleted residuals, there's not anything much going on. So I wouldn't be too concerned about things going on in this set. Really, the biggest issue here for us is the fact that our outcome variable isn't actually a continuous variable. Again, it's ordered categorical. All right. So this is a lot. Questions on what we've done or any of the conclusions that we've drawn based on this?
Just a quick question.
Yeah.
I think it does look different to the handout. The handout we printed out.
Yeah. What?
So should it be like the same?
It'll be a little bit different. Yeah. So my plot here is I'm using an older version of SPSS. So there'll be some minor stuff. So don't worry about sort of it being exactly the same. Just sort of focus on the process piece. All right. Okay. So the last thing that we're going to do is we need to start thinking about collinearity issues. Okay. So what I'm going to do is I'm going to go through. I'm going to analyze, correlate, bivariate, and I'm going to look at my natural log of my role functioning, pain, opiate use, PTSD. I'm going to paste those in there. And I'm going to go through and look at this, run those correlations. And Siley, what am I going to look at here? What am I looking for in this correlation table that might give me pause? I'm not saying that this correlation table will give me pause, but what am I looking for that would be a problem within this correlation table?
If anything was highly correlated with one another in terms of your independent variables.
Yeah, perfect. Right on the money. I'm wanting to make sure that my predictors aren't super highly correlated, right? Now, a rule of thumb is like 0.9. If you got any correlations between the variables that's hitting 0.9, you've got lots of problems going on, right? Correlations, we see a fairly strong correlation between my role functioning variable and pain severity. That just suggests that maybe this is has a strong association with pain severity, has a strong inverse relation with the natural log of role functioning. So I'm not too concerned about that. What I'm more concerned about is down here, correlations between pain severity, opiate use, PTSD stuff. Looks like opiate use has a modest relationship with pain severity. It's kind of what we would expect. But overall, nothing concerned, at least in terms of bivariate correlations that are too big that would indicate multicollinearity. Okay, what's the one limitation of just inspecting bivariate relations in terms of collinearity stuff? Any ideas?
It's not showing us like the relationship of all of them together.
Yeah, what I could have, right? If I take, let's say, a column of random numbers, and then a second column of random numbers, right? Are tomorrow those two columns of random numbers correlated with one another?
Can you repeat that?
Yeah. Let's say I have a column of random numbers. So I have a random variable 1, random variable 2. Are those two variables related to one another?
They could be.
But if they're truly random, should they have any sort of... No, right? And so variable 1 and variable 2 are not correlated. But let's say that I then create variable 3. And variable 3 is the sum of 1 and 2. Okay? If I go through and I look at the correlation between random variable 1 and variable 3, are those two going to be correlated? Nope. Is 2 and 3 going to be correlated? Nope. But if I throw all three of those variables in the mix, I'm going to have collinearity, right? So even though in my bivariate plots, x1, x2, and x3 are all completely zero correlated, all three of those together are collinear with one another, right? Because if I know x1 and I know x2, then I know for sure the value of x3 in any other combination, right? And this is where, particularly if we have large a number of predictors, where we want to go through and look at true multicollinearity, where we've got potentially linear relations between a number of different variables. So what I'm going to do is I'm going to go back up. Remember this sort of the main regression model that we ran way up at the top to get all of our residuals and all of that type of stuff, right? I'm just going to repaste this, and it's going to resave residual values and stuff like that, but I don't really care about it. So I'm just going to rerun my regression model. And what I'm going to do is I'm going to go down through here, and I'm going to look at, on my coefficients, I'm going to see a point in my table called collinearity statistics. Okay, and what I'm looking for is going to be my tolerance values and my VIFs. Okay, tolerance and VIF are basically the same thing, just in different metrics. Tolerance is just going to be the is going to equal 1 minus the multiple correlation of my, let's in this case, my opiate predictor regressed on my other stuff. Okay, and so what I'm looking for here, if I have a tolerance value that's 0.10 or smaller, that's suggesting that I've got a very, very strong correlations among my predictors that would be problematic. Okay, and so if we go back to my collinearity, multicollinearity statistics, again, tolerance is going to be looking at values less than 0.1. Again, if you get anything even close to that, that's going to be problematic. Variance inflation factor, if you get values bigger than 10, you should be concerned. But if you get anything even close to that, you should already be concerned about this. And so if we go through, and what either one of those would mean is just we have very, very strong intercorrelations among our predictors. Okay. So Chris M., am I seeing any concerns here with my tolerance or my VAF values?
You're not.
No. So things are looking okay. So, and I suspected as much based on my correlation table, but it looks like even in multivariate space, I'm not having problematic issues with my collinearity. And the problem with collinearity is that it's going to make my standard errors really big and really unstable. It doesn't, collinearity doesn't bias my point estimates, my coefficient. My regression coefficients are still unbiased. But what happens is my standard errors start to get really big and jump around. And so what can happen is I can have something that has maybe a standardized coefficient of 0.56, right? Something that's really big, but associated with a very large p-value, which would suggest that maybe my standard errors are sort of getting thrown off by collinearity. Okay, so here we look at tolerance VIF, not seeing any problems. But if I did see a problem there, then the question becomes what combination of variables are becoming problematic and driving multicollinearity. What we can do in that case is start to look at down here my collinearity diagnostics. And what I'll see here is I'll start to see if I see a case with an eigenvalue that's very close to 0, combined with a condition index that's greater than 30, and variables with a variance proportion that are greater than 0.50 on a couple of different variables, that's going to start to suggest, tell me what combination of variables are causing me problems. So here, if I go down through and I take a look at my collinearity diagnostics, I see eigenvalues, so my smallest one here, and these will always decrease, so your last eigenvalue will be small, but the condition index isn't over 30, it's 9. And if I look at my variance proportions, I don't have two of these that are exceeding 0.5, right? So this is what we can go through and use. If I do run into a problem with multicollinearity, I can go down through and start to use this to kind of figure out what specific combination of variables is causing my problems. Okay.
So
Questions?
This is dimension 4. So what if those indicated that there was multicollinearity? What does the dimension 4 mean?
Oh,
ATS.
so this is just this is kind of like a factor analysis type of thing. It's pulling out unique components, and so it's just looking at shared variance across your predictor variables. And so for your purpose, Sean, if you want to, at a later point in time, get into what's kind of going on with these eigenvalues, actually, this Friendly and Kwan paper does a nice job of talking about what's actually going on with this stuff. For applied purposes, we're probably primarily going to use this to just kind of tease apart what things are sort of associated where it's going to be more diagnostic than anything else. Okay. So basically,
there is a problem. It doesn't tell us which combination is the problem.
Yeah, no, it does tell us which combination. So let's say, okay, so here I have some, like in this example, I have more collinearity between my variables than I did in the problem that we're working with. But let's say that I found that these tolerances to be too low, and I was like, oh, what's really going on? What I could do is I could say, okay, well, here's my smallest eigenvalue, and that is very close to 0, associated with a condition index of over 30. And so what it looks like based on this is it's some combination. What's driving collinearity up here looks like a combination of Bass reward responsiveness and NOS total. There's something going on in that combination that's problematic. Now, if I had a lot of predictors,
the ones that are over 0.5 are the ones that part of the combination that's
yeah,
the problem.
Yeah.
Okay.
And so that's what we're looking at. And so this can start to become an issue if I'm running, again, like in marketing or econ or some other sort of applied, if I've got a very large a regression model with a lot of predictors in there, I might have 20, 30 predictors, and who knows what combination of things happen to line up to create collinearity. This can be a way I can go through and start to tease that out. Okay.
Okay, thanks.
Yeah. Other questions?
So just a quick clarification.
Yeah.
The tolerance and the VIF are basically like just different ways of looking at the collinearity, kind of like S values and VFB.
Yep, yep. They're exactly the same thing. Tolerance is 1 minus the squared correlation of that predictor regressed on all the other ones. And then tolerance is just the inverse of that. It's 1 divided by your VIF is just 1 divided by your tolerance. So, and you can get into more technical interpretations of VIF. If you take the square root of my VIF, that's going to give me, so if I got a VIF of 2 and I take the square root of 2, it's going to give me 1.41, suggesting that I'm seeing a 40% increase in my standard errors relative to if I had uncorrelated predictors, right? So that just starts to get into a little more technical, sort of what's happening. For your purposes, I won't need you getting into that much unless you want to deep dive into that. You're just looking through and saying, do I have really large VIFs or very small tolerance values? Okay. All right. So last thing, so that does it in terms of our screening stuff. But what we want to do is we're going to go through and try and sort of make sense of all this. Yeah. So what we want to do is here's, again, giving you an example of potential write-up here. So again, screening, no problematic values in terms of accuracy, plausibility, no missing data, right? Univariate distributions. Here's Skew, talking about Skew, histograms, and Boxplots for my predictors. But then I've separated role functioning here as being problematic. Identifying role function is actual ordinal variable taking on just 5 values. Majority, 78% of cases are reporting 0. Everything else is continuous tail. So talking about kind of problems there, saying that we natural logged role functioning. Things got better. Histogram and Boxplot are still gross because it's still an ordinal variable, but it's looking better. Opiate use balanced. Always remember don't forget your categorical variables. Here we're saying opiate use is balanced, so we're okay with that. Talking about our univariate outliers, nothing much going on there, not concerned with that. Bivariate associations, looking at linearity, homoscedasticity, no evidence of nonlinearity. Bivariate plots, little evidence of heteroscedasticity, so that's looking okay. Our residuals approximately normal based on our MPP and our histogram. Some positive skew. Residual by fitted values. Again, this is my residual plot. I've got an odd lowest, but it doesn't give me real strong evidence of heteroscedasticity. But it's a weird ordinal dependent variable, so that complicates stuff. Discrepancies are all looking fine. Leverages, I found 5 cases that exceed 3 times the average of my centered leverages. Alicia, when you're doing this in Stata, you're using just regular leverages, so just be aware that your values are going to change a little bit. We've got 3 cases that we decided to sort of take a closer look at. Case 310, low pain, coupled with high PTSD. 221 was just severe PTSD. 202, low levels of pain. We're saying this might be something to look into, but really we're not too concerned about things. Again, if we had cases that we were concerned about, what we can do is go through and run our model with and without those cases and kind of see what happens. Okay. Influence, Cook's D several cases, 14 exceeding our benchmarks. Histograms and box plots identifying. So these as being the most extreme influential cases. But when we look at our combination plot, nothing really going in there that suggested big issues. Multicollinearity, bivariate plots, VIF, and then our recommendations. Okay. So again, predictors looked okay. Role functioning was ordinal. natural log transformed. Residual plot looked weird, but that's probably a function of our categorical outcome. Number of cases identified that we might want to look into, might look at the model with and without it to see if there's any big changes. But pulling it all together, you got reasonable adherence. Measurement of role functioning is the most problematic. And again, as I said at the very front, if I were to run into these data, what I would do is I would probably just say off the bat that a standard multiple regression isn't the best analyses for this. We have analyses, and again, Nick, with the type of stuff that you do, this is the type of thing that we would often run into. These type of an outcome where we would probably want to switch over to maybe to, as Sean had suggested, maybe just dichotomizing it. But if we thought there were meaningful deviations between our higher levels, looking at some sort of count regression model that accounts for like zero inflated Poisson and zero inflated zero binomial types of things that specifically address these types of data because they come up on some regular basis within certain types of stuff. But in terms of our screening, everything else looked pretty good outside of just the fact that our dependent or variable looks sort of maybe not so great. Okay. So that's a lot. But as we start to get into these models that have a lot of different variables, just wanted to make sure that we're going through. And any time you're going through, I can tell you right now with your theses, with your dissertations, with papers, the majority of your time and analysis is going to be spent on screening, trying to figure out what the hell's going on with your data. But the good news is by the time you finish up with this, you're going to have a really, really intensive and good understanding of what's going on in your data. If there's weird stuff, you'll be able to identify it. And this can often be an opportunity for generating ideas for future directions, sort of understanding your phenomena a little bit better and how everything fits together. So it can be a pain, but it gets easier the more that you do them. And if you have a good system and syntax to work through, it starts to move through pretty quickly. Okay. Questions? How's everybody feeling? Exhausted after 3 hours of stat? Yeah. Okay. Cool. So what this means is we'll finish up with that last set of slides next week. So our regression set won't be due next Friday. It'll be due sort of the following Friday, which is fine. But do get an early start on this. Start working through working through particularly the screenings. That's probably going to take you a fair amount of time. If you have questions, let me know. And again, had posted the screencast walkthrough of our lecture today. And if you go to the description, if you hit show more, I've put markers for different things. So if you're confused about the combination plots or the discrepancies in YouTube, you can go down through, hit the description, pull that down, and just click to, and it'll jump you right to this spot in the video where we finished up with stuff. So that'll be, so you don't have to surf around in that. Okay. Questions? Okay, cool. It was good to see you guys. Happy to be back in the mix. I feel like this went about as good as it could. I think it lends itself all right, given that we're doing a lot of online stuff and working through statistical programs. But if you're into snags, let me know. Otherwise, I'll see you all on Wednesday. Sound good? Awesome, folks. Oh,
Can I jump in to make just one quick announcement?
Yep.
So I'm moving virtual to all of my office hours, so if you need me, feel free to text or email me tomorrow between 10 and noon, and we can hop on a call or jump on Zoom if you need that. And if those hours don't work for you for any reason, you can always email me, and we can set up a time to meet. That's it. Thank you.
Cool. All right, folks. Again, it's good to see everybody. Sort of being shut off and alone is kind of sucks. Working from home isn't all it's cracked up to be 100% of the time. So, but stay safe, stay healthy. Let me know if you're running into snags, and otherwise, we'll catch you on Wednesday. All right, we'll see ya.